Okay, so it's my pleasure to welcome to our seminar Marco Benini. He's he's an assistant professor in Genoa. Before that, he did his PhD in the University of Pavia and did some postdocs in Scotland and Germany, and then before coming back to Italy. So he's going to talk to us about smooth one-dimensional algebraic quantum field theories. So please go ahead.
Thanks, Igor, for the presentation, and thanks for the invitation to speak about this subject. So let me quickly give an introduction or an outline of what I'm going to talk about. So first, I will recall what is an algebraic quantum field theory. That is at least to give you some background of what is going on, even though from the list of from the audience, I think many of the many people will already know what I'm going to say, but it's still good to kind of set up conventions. I will then introduce, maybe very briefly motivate and introduce what I want to talk about, namely a smooth refinement of what it means for or what it means for an AQFT or an algebraic quantum field theory to smoothly assign observable algebras to smoothly parametrized families of spacetimes. This will require replacing categories with stacks. This is kind of the short way of saying it. I will then describe the stack instead of the category of one-dimensional spacetimes. We will look at the easiest example, and the space here goes in within brackets because there's just one dimension. So space is a point and time is a line. I will explain why this example is considerably simpler than any other than the higher dimensional examples. I will then introduce the stack of unital associative star algebras over the complex numbers. That's the replacement, the smooth replacement for the category of star algebras, the usual category of star algebras. And then I will introduce smooth one-dimensional AQFTs, the stack of smooth one-dimensional AQFTs as a mapping stack. I will then briefly say, this depends on how much time is left. I could either do a very quick overview of how to construct linear examples of smooth one-dimensional AQFTs or go more into the details. In summary, what is going on is the following. One needs a replacement for the canonical commutation relations, and this is a smooth quantization functor implemented by a smooth quantization functor. Then one, in order to produce examples, actual examples, one needs green operators as usual and initial value problems as usual, but now parameterized smoothly. And then I will outline certain open problems in how, which involve going beyond dimension one. Yeah, some stuff is fairly clear, and some stuff is less obvious. Yeah. Okay, so let's start from what is an algebraic quantum field theory. This is an axiomatic framework to mathematically formulate what it means to be a quantum field theory. There's a lot of examples which kind of fall within the same structure. Algebraic quantum field theory originated from modeling quantum field theories on Minkowski spacetime, and this is the work that goes back to Haag and Kastler in the 60s. Then many other people, of course, worked on this, and one important extension of this framework involves curved spacetimes, and this is originally probably, I would attribute it to Brunetti, Fredenhagen, and Feach, and Hollands and Wald. But of course, again, many other people. The list is super long, and there are also applications to chiral conformal field theories, Euclidean field theories, and probably much more. Yeah. The crucial thing is the structure that is kind of lying in the background, and the structure that is lying in the background is the following. A quantum field theory is encoded by a functor, this letter A, and this functor is defined on a category of spacetimes, of m-dimensional spacetime. The subscript m here denotes the dimension. To each spacetime, it assigns a star algebra, associative unital algebra equipped with reversing involution over the complex numbers, and these are the algebra of observables. So the quantities that you are supposed to be able to observe or on a given spacetime. So this, I mean, just saying functor encodes quite a bit of structure, but is not yet enough for physical reasons. One also requires additional axioms, which encode causality, time slice property, and in some situations you want more, something like additivity. I won't list them all. I will just focus on causality and time slice for the moment. So what is Einstein causality? Einstein causality means the following. So you have, do you see my pointer? Okay, good. So yes. You have a big blue, light blue spacetime, this M. Inside this big spacetime, you have two smaller spacetimes, M1 and M2, and they are embedded. However, they are embedded in such a way that there's no way they can causally communicate. There's no way that there can be causal communication between the two. Yeah. So any light ray that is emanating from M2, say, can never encounter M1. Yeah. This says that, and then the requirement is the following: the subalgebras that are attributed to M1 and M2, sitting inside the big algebra assigned to M, they commute with each other. Yeah. So this encodes the idea that nothing can travel faster than light. So space-like separated observables act independently of each other, namely they commute in the big algebra assigned to the larger spacetime. Yeah. This is Einstein causality, and the second physical requirement is the time slice axiom, which is kind of a dynamical law. So what do you do is the following. Inside the category of spacetimes, of m-dimensional spacetimes, I don't want to devote too much time to the details of this category because we don't need them. Also, mainly because I will just go to dimension 1 very soon. So inside this category, you can select a certain class of morphisms. They are called the Cauchy morphisms. And the way to represent them is the following. You again have a big spacetime, M prime, and you have a smaller spacetime, M. However, this smaller spacetime, M, is in a sense sufficiently wide in the spatial direction, so that it contains what is called a Cauchy surface of the ambient spacetime. This Cauchy surface is the place where you can detect initial data for a certain PDE, for a certain hyperbolic PDE problem. Yeah. So when because the smaller spacetime contains already the initial data, provided the Cauchy problem is well posed, the smaller spacetime M already knows everything about the theory on M prime. Yeah. So the statement is the embedding of F, the embedding F, this black arrow of M into M prime induces an isomorphism at the level of observable algebras. And this is a dynamical law, the time slice axiom. Okay, so far so good for recalling what is an algebraic quantum field theory. Now let's talk about smoothness in an easier case, in the easiest case possible, which is dimension 1, just time if you want. So why do we want smoothness? In my opinion, the AQFT axioms are very nice, but they don't address one interesting question, or maybe two. The first question is, do AQFTs respond smoothly to smooth changes of geometry? This we don't know. I mean, from the axioms, we can't say. Yeah? There is no a priori reason why they should. And the second question that the axioms don't allow you to answer immediately is what it means to be a smooth family of AQFTs. I will try to give an answer in the one-dimensional case and point towards how to extend this beyond dimension 1. So the smooth refinement uses more or less well-established trick in category theory, which says if you want to encode smoothness, replace categories and functors by smooth categories and smooth functors. And now I have to tell you what it means to be a smooth category and what it means to be a smooth functor. And the idea is the following: you encode smoothness by the so-called functor of points perspective, which means you replace categories by stacks of categories over the site of manifolds with open covers. Yeah, this is kind of categories parameterized by smooth manifolds in a consistent way, and this consistent way captures smoothness. We will see this later on concretely. So why do I want to focus on dimension one? I want to focus on dimension one because in this case, causality is trivial. Yeah, causality, trivial causality simply means that AQFTs are basically just a functor category. The category of functors from one-dimensional spacetimes to star algebras. And this is, I mean, it's very easy to understand what this functor category is. It's just functors and natural transformations, no more, no less, no properties required. Yeah, no properties required. And this is a considerable simplification that we will use. Then we will follow the following three-step process in order to define smooth one-dimensional AQFTs. So we will first replace the category of one-dimensional spacetimes by the stack of smooth families of one-dimensional spacetimes. We will then, this is the source of the functor category that we used in order to define one-dimensional AQFTs. Then we need to replace the target category. So we will replace the category of star algebras by the stack of smooth families of star algebras. And then we need the last thing we need to replace is this functor category. Yeah. Instead of the functor category, we will use the mapping stack construction, which provides now our definition for smooth families of one-dimensional AQFTs. So let's move forward. I already said the word stack too many times not to recall what a stack of categories is. So a stack of categories is the following. It's a pseudo functor. Pseudo here is important. Defined on the category of manifolds. Yeah, it's contravariant. It takes values in the two category of categories. Yeah, we need the two category of categories in order to speak of pseudo functors. So what concretely X does? It does the following. It assigns to a manifold, which I call U, a category XU. Yeah, kind of the category of viewpoints of X. We will use sometimes this way of saying. Also, to a morphism, to a smooth map between manifolds, if you want, it assigns a functor. But notice that that U and U prime are reversed. This is contravariancy. Yeah. That is not the full structure. This would be the full structure if we wanted to describe a functor, but we want a pseudo functor. And the pseudo functor kind of, instead of having a property encoding functoriality, so compatibility with composition and identities, it has additional structure. And this additional structure consists of natural isomorphism, which witness the compatibility with composition and identities. And these additional axioms, these additional data, which are natural isomorphisms, are subject to certain coherence axioms. If you know what a monoidal category is, the axioms for a monoidal functor are similar to those. Yeah. So far we just described what a pseudo functor is. We didn't say what a stack is, because in order to design stacks, we need to encode a certain descent property. Yeah, similar to pre-sheaves versus sheaves. Yeah. And what does this descent condition say? So you have to take a certain manifold U, you have to take a certain open cover of your manifold. Yeah, anyone would do. Any U and any cover of U does the job. And you require the following. So because you have a pseudo functor, you can evaluate X on U, and this gives you a category, but you can also evaluate X on your cover. And this gives you a new category, which is called descent category, whose objects I described down here. Oops, sorry. So what are the objects? They are kind of an object for each patch of the cover, plus transition functions on the double overlaps. And the transition functions are subject to the usual co-cycle conditions. Yeah, like when you want to glue vector bundles or principal bundles. I mean, it's very much the same thing, just abstracted away. Yeah. The usual definition, but inside a generic category, kind of. Yeah. And the requirement, so because X is a pseudo functor, there is always a functor that kind of takes global data and restricts it to local data. This pseudo functor becomes a stack, namely satisfies descent, when this restriction functor is an equivalence of categories. Yeah, so it says that you can always reconstruct global objects by local objects. Yeah, essentially. Very much like sheaves versus pre-sheaves. Yeah, you kind of take local sections and you know that you can glue them to produce global sections. Here it's like gluing, but up to isomorphisms. So what is the prime examples of such a thing? Well, the stack of vector bundles. What does the stack of vector bundles do? You take a manifold and you assign the category of vector bundles over U. Yeah. And you can, for example, take a vector bundle, chop it down in smaller vector bundles over a cover of the manifold, and you can glue it back if you want. Yeah. You can even more. You can just provide vector bundles over a cover with transition functions matching the vector bundles on the double overlaps, and provided a certain co-cycle condition holds, you can glue this local data to a global vector bundle. This is what is going on here, precisely what is going on here. So I just described the objects of the two category of stacks. In a two category, there is more than just objects. Yeah, there are also the one cells and the two cells. The one cells, or morphisms, I will call them, are the pseudo-natural transformations, and the two morphisms are the modifications. We won't encounter any modification explicitly. We will definitely encounter pseudo-natural transformations between stacks, but I will mention them later on.
Marco,
yeah.
But at this point, I was just wondering, I think there's a different definition of stacks where instead of mapping into a category, you might map into
groupoid.
Groupoid, yeah. So, and the main difference in a groupoid is that all the arrows are invertible. So are you relying on the non-invertibility of some arrows?
Because we do pseudo functors, this mildens this difference, yeah, because like the further structure is always encoded by natural isomorphisms, yeah. Mm-hmm. But indeed, we allow for more. Yeah, we really need stacks of categories because, for example, we want to replace categories and not groupoids. Let me go back. Yeah, so this guy is a category and not a groupoid, and this is the thing I want to describe as a smooth object. Hence, I really need stacks valued in categories. As you will see, my stack, the global points of my stack later on will be exactly this category. But then I really need stacks valued in categories in this sense, yeah?
Okay. So you're right. So you're relying, so to make the analogy with vector bundles, you're looking at constructing the stack of vector bundles of any rank.
Exactly, yeah, with maps that are not necessarily isomorphism fiber-wise.
Yeah. If you were to restrict the rank of the fibers of the vector bundles you're considering, then you could reduce the target to a groupoid of the transformations between vector spaces of the
Still you have to decide that you only want fiber-wise isomorphisms, yeah. Mm-hmm. Because if you still allow for non-injective and non-surjective maps, yeah, you can, even with the fixed rank, you can have just a stack of categories instead of a stack of
okay, but then I would not be aware of inclusions of vector bundles.
say again?
Then that stack would not be aware of the inclusions.
Exactly.
Of the
Yeah,
bundles.
exactly.
Or projections.
Yeah,
okay.
yeah, or projections. Yeah, that's right. Yeah, so we need stacks valued in categories. No, this is important here because we just want to model smooth categories and not smooth groupoids. Yeah, the things we want to work with are not groupoids.
And sorry, maybe you defined it. You did say it, but maybe I missed it. So the pseudo part of the pseudo functor is that it satisfies the functor axioms up
natural
to
isomorphisms, prescribed natural.
So if you consider the arrows in the category as kind of like the redundancies or symmetry, so up to those, up to that data.
Yeah. So this is prescribed data. This is not. I mean, this bullet point is not a property. Yeah, this bullet point is data. The property is subject to coherence axioms after the comma. Yeah, that's the only property in this structure. Yeah, usually you say this is the first one is data, the second one is data, and then there's a property. Because here we go up by one, yeah, we have one further layer of data, and the properties are transferred one level up. Yeah. It's the usual counting in category theory, in higher category theory, if you wish. So let's do some constructions involving stack of categories that are needed later on. We already said that we certainly need mapping stacks in order to do something. Yeah, in order to define smooth one-dimensional AQFTs, we need mapping stacks because previously we needed functor categories. Yeah. Okay, so there's something even more basic than mapping stack that we need in order to even interpret what we are doing. And this is the two-Yoneda lemma. What does the two-Yoneda lemma tell you? Well, it tells you that there is a two-functor which takes manifolds as inputs and regards them as stacks. How is this performed? It's in a kind of dumb way. Yeah, you take your manifold U and you look at all smooth maps inside U. Yeah. This gives you a way of interpreting any manifold as a stack. This is just because we took stacks over manifolds. This satisfies descent because you know smooth functions give sheaves. Yeah. The important fact is that this is a fully faithful embedding into the two category of stacks, which kind of means you can regard manifolds as manifolds or equivalently embed them into stacks, and they are kind of the same thing. Yeah, what you see is kind of the same thing. Even more, you can look at this category. Yeah, so ST, the two category of stacks is a two category. So whenever you take a stack and another stack, the maps in between give you a category. Yeah, what we called previously pseudo-natural transformations and modifications. This is the category of pseudo-natural transformations. From this stack, you underline into X. And a fact is that this category is equivalent to the category, I didn't want to go forward, to the category of U sections of the stack X. Yeah. What does this tell you? It tells you that you can interpret this category XU as the category of smooth U families in X. By smooth U family, I mean a map of stacks from U underline into X. Yeah. This is interpretation of what we are doing in a sense. So we will need, in order to talk about the mapping stack, we need a preliminary ingredient, which is the product stack. And the product stack is very easy to understand, at least in this framework, because we are kind of one-dimensional. This is easy. If we were to go higher dimensional, I hope I will have time to talk about it later on, this will become more complicated. But the complication comes from the fact that we don't any longer, we will not be satisfied with stacks of categories. We will need stacks of something more interesting, more structured than categories. And this is the source of the complication. Okay, so product stack, you take a stack X, you take a stack Y, you take their product, which in this case is called Cartesian product because this is a Cartesian monoidal structure. What it assigns to a manifold U is just the Cartesian product of the categories XU and YU. So a smooth U family in the product stack X times Y is just a pair of smooth U families. Yeah, one in X and one in Y. Very easy. Now the mapping stack. The mapping stack.
Excuse me, before you go on, can I ask something about the two-unit lemma very quickly?
Yeah, sure.
When you okay, you define the the unit functor like this, but okay, ordinarily this would make sense for me. Like if you plug in manifold V, you're looking at like maps from V to U.
Yeah.
Okay, but you define your stacks to be valued in categories, or the two category of categories.
Yeah, that's right. So this
ordinarily, like the stacks will land in simplicial sets, like simplicial sets. So this would make sense. But how do you like interpret this category? Like, do you put
this man VU I interpret as a discrete category, so as a set regarded as a category which only has identity morphisms. I mean,
I thought you could do more, but okay, that was the question.
Yeah. Okay. So yeah.
Okay, thank you.
Sorry for not saying that explicitly. Yes. So I regard this set as a discrete category, a category which only has identity morphisms, and the objects are this set. Yeah. Indeed. Yeah, so the mapping stack, how do we perform the mapping stack? You take X and Y and you want to define a new stack, map X, Y, and you do this as follows. So you evaluate it on U, and then you use the product stack to produce a new stack, and the two-unit lemma. Yeah, you take U underline, this is a new stack, times X. That's the product stack, and then you take the category of pseudo-natural transformations and modifications from U underline times X into Y. Yeah, you can do your checks and prove that this is again a stack. It's a pseudo-natural transformation, kind of obviously, yeah, and that it satisfies descent. There's a bit of work to do in order to check that. So what it means, it gives you, it means that U families, or smooth U families inside the mapping stack are just stack maps from U underline times X into Y. Yeah. So you can kind of always move X back to the source in a sense. Yeah. This is why this definition is very practical and convenient in a sense. Okay, so the next steps for us are to construct this Log1 infinity stack of smooth families of one-dimensional spacetimes. This is what we need. Second step is to construct the stack of smooth families of unital and associative star algebras where the star reverses products. And then we just compute, or well, we just define the smooth one-dimensional AQFT, the stack of smooth one-dimensional AQFTs using this mapping stack construction, and we will explore it a bit. So I see that already kind of half an hour passed by, so I will try to become faster. Let's see if I manage. So let's describe briefly what is the stack of one-dimensional spacetimes. So a smooth U family, I define as follows. It's a pair pi and E. Pi is a locally trivializable fiber bundle from M. The total space is M and the base is a given manifold U. Yeah. And the typical fiber of this locally trivializable fiber bundle is an interval in the real line. Yeah. So one-dimensional, kind of a time interval if you want. Yeah. But this time interval kind of varies and is parameterized by the base points in U. Yeah. So each fiber is a different copy of a time interval. What makes the distinction between the different intervals is the fact that we provide certain vertical geometry on this fiber bundle. So on the fibers of the bundle we define, or on the total space we take one form which is however vertical. So the leg, there's only one leg that points vertically along the fibers. Yeah, and it's non-degenerate. Hence, it tells us kind of what is the scale. What is the time scale fiber-wise, and where does the future point? Yeah, whether up or down, kind of. Yeah, or it tells us, let's decide that future is where the leg points. Yeah, where the only leg points. This is how we provide geometry on this. Yeah, this is one way of providing geometry. A morphism between two smooth U families is just a fiber bundle map. And we require this fiber bundle map to be an open embedding of the total spaces, which preserves geometry. Yeah, there are different ways of defining this. And one is lucky that there's at least 3 different ways which are actually equivalent to each other, but they are kind of convenient for different purposes. I gave you the global definition, which makes very mysterious why the thing I'm constructing is actually a stack, why it has descent. There's a local definition, which we are lucky is equivalent and allows you to prove that the thing I'm defining gives you a stack. So I'm hiding this, of course, in my slides, so I'm not doing the details of that. But it's clear that when you pull back fiber bundles, you get new fiber bundles, and pulling back twice is up to isomorphism, like pulling back along the composition. Yeah, this provides the pseudo functor log1 infinity log1 infinity. Yeah, this pseudo functor, which to each manifold U assigns the category log1 infinity U we just defined. Yeah, we just defined objects, smooth U families, and morphisms of this category. Then you have to do a bit of work, which involves kind of finding an equivalent definition which looks more local, yeah, in order to prove that indeed this pseudo functor is also a stack. Yeah, the key point is on the level of objects, the key point is bundles glue via transition functions, of course. And once you glued the bundles, you can pull back the local forms to the patches of the global bundle you constructed, but forms are a sheaf, so you can glue them on the nose and you get a global vertical one form, which is again non-degenerate, giving you the geometry on the global object. What is less obvious here is how do you glue morphisms? And this has to do with the fact that the definition I gave you is very global, but there's an equivalent definition which becomes extremely local. Yeah. Stop for a second. Look at the global points of this stack. Yeah. Now the base U is just a point, so there is just one fiber, and this one fiber is an open interval in time, right? A time interval, and on this time interval there's a gadget to say where does the future point and what is the scale that you use in order to measure time. What's your clock, in a sense?
Marco, so this capital E, you could just say that it's the differential of the proper time on the time interval.
If you wish,
right?
yeah, yes. Yeah, exactly. Yeah, the differential of proper time, yes. Yeah, exactly. Okay, so the second gadget we need is the replacement of the category of star algebras. So we need a stack of smooth families of star algebras. How do we do that? There's a naive attempt that one can perform. One can consider the category of vector bundles, and this is actually the most naive, the first thing that comes to mind. Yeah, you take the category of vector bundles, of complex vector bundles, over a manifold U. This indeed provides a stack. We already mentioned this fact. There's an issue that vector bundles have finite dimensional fibers. Yeah, unless you work with topological vector bundles or with potentially any locally convex topological vector space as fibers. Yeah, the problem here is when you work with vector bundles with finite rank vector bundles is that QFT algebras, quantum field theory algebras, are never finite dimensional. Yeah, even in one dimension, even when space-time has one dimension, you have quantum mechanics, and quantum mechanics algebras are most definitely not finite dimensional. Yeah, so this is the issue here, and the replacement that we take for this issue is the following. Instead of looking I mean, you can, there are many options to replace the category of vector bundles. One I already mentioned, but this is not the one I'm choosing now. Instead of vector bundles, I'm taking something that you can interpret in a certain way as vector bundles, yeah? And these are sheaves of modules, yeah? Sheaves of modules over the sheaf of functions on a manifold, yeah? This, again, is a category, the category of sheaves of modules. And it's a result very well known by Kashiwara and Shapira, that the assignment of the category of sheaves of modules to a manifold gives a stack again, yeah? Kind of the finite rank, the free finite rank gadgets in this category are precisely the vector bundles, yeah? The usual finite dimension, finite rank vector bundles. Serre-Swan duality, yeah? So you can, because we took complex guys, you can put an involutive symmetric monoidal structure on each category of sheaves of C infinity modules, yeah? What you can observe, it's a pretty straightforward observation, is that this gives you, again, a stack. However, instead of being valued in just the categories, it's valued in involutive symmetric monoidal categories. Why is this interesting? It's interesting because we want to form star algebras. And what are star algebras? Well, they are just reversing star monoids in a given involutive symmetric monoidal category. So when we take reversing star monoids in our category of sheaves, we immediately define the category of star algebras, yeah? And because taking reversing star monoids gives a two-functor, and because sheaves, the assignment of sheaves was a stack, it's automatic that star algebras also form a stack, yeah? Very good. So we have our replacement. Now stop for a second. Stop for a second with the formalities. Think of the global points of this stack, yeah? The global points of this stack are very easy. Sheaves on a point are just vector spaces, yeah? Complex vector spaces. And the complex, and now you take star algebras in complex vector spaces, all of them, yeah? Or all algebraic complex vector spaces, and you take star algebras in all algebraic, you take star monoids, reversing star monoids in all complex vector spaces. You precisely recover algebraic star algebras, yeah? Okay, so now we have everything we need in order to define the stack of smooth one-dimensional algebraic quantum field theories. We already said that we want to define this stack using the mapping stack of between the two gadgets we just introduced, yeah? Which we agree they are at least one replacement, one smooth replacement of the ordinary categories that you would work with, simply because the global points of these stacks are exactly the usual categories you would work with. Let's look at this definition, yeah, for a second, in order to interpret what are the global points of this definition, which I will call smooth one-dimensional AQFTs. So the global points are just, we said this before, they are just stack morphisms that I denote by this letter A, mapping the zero-dimensional manifold, the point, inside our mapping stack. Now, by the observations we did when we recalled the two Yoneda lemma, we can equivalently look at this stack morphism as an object in the category that the stack of smooth one-dimensional AQFTs assigns to the manifold point. Yeah. What does this mean? By definition of mapping stack, this is just a stack morphism from the stack of one-dimensional spacetimes into the stack of star algebras. And now we can look at this closer explicitly. Yeah, we said that stack morphisms are pseudo-natural transformations between the pseudo-functors underlying the two stacks. So explicitly, we have a pseudo-natural transformation. What does a pseudo-natural transformation do? It assigns to a certain manifold U a functor between the corresponding categories, yeah? And this functor, well, pseudo-natural transformations are kind of the one step higher analog of natural transformations. So instead of having a property on the nose, a certain commutative diagrams, you provide further additional data. And these further additional data are encoded by natural isomorphisms, that witness pseudo-naturality. These additional data are now subject to coherence axioms that involve the natural isos and the structures coming from log1 infinity and star alg infinity, yeah, the stacks. Okay, so observation. Look at the component of A that corresponds to the point manifold, yeah? So this is A subscript star, according to the notation we introduced here, yeah? We already said that the global points of the stack log1 infinity are precisely the one-dimensional spacetimes, the usual ones. And we already said that this stack assigns the ordinary category of star algebras. And then we have a functor between the two. And this is precisely an AQFT in the usual sense, yeah? The ordinary one-dimensional AQFTs, non-smooth ones, were just functors, yeah, like this. What is the further structure that is encoded by this mapping stack is the other components, the non-point components. And the non-point components precisely encode how the smooth one-dimensional AQFT responds to evaluation upon a smooth U family of one-dimensional spacetime. So now you provide a family of one-dimensional spacetimes that is parametrized by a certain manifold U. And your smooth one-dimensional AQFTs gives you back a smooth U family of star algebras instead of just one, yeah? Okay, there's more you can do. This was the first question we had, what it means for an AQFT to respond smoothly to smooth variations of geometry. The second question was what it means for to have a smooth family of one-dimensional of AQFTs, say, yeah. And this we can also answer. How do we answer this question? Is by looking at maps from, say, a certain manifold U tilde inside our mapping stack of one-dimensional AQFTs. These are just stack morphisms. B from U tilde underline, we use Yoneda, yeah, inside the stack we defined. 2 Yoneda allows us to interpret this stack morphism as just an object in this category, AQFT1 infinity evaluated on U tilde. Yeah, this is a category, and we take an object of this category. Because of the definition of mapping stack, this we can equivalently interpret as a stack morphism from U tilde times log1 infinity into the stack of star algebras, yeah? And then we can again use the mapping stack, but now we exchange who's the source of the mapping stack, yeah? Originally it was log1 infinity, the source of the mapping stack, and now we will instead use log1 infinity as the source of B, of the stack map B, and we will instead use as the source of the mapping stack U tilde, yeah? So we regard B as a stack morphism from log1 into the mapping stack of U tilde inside the star algebras. This is very useful, as we see immediately, because it's easy to describe these data explicitly and to understand what they are. So what are stack morphisms? Let's say this again. They are pseudo-natural transformations, and pseudo-natural transformations assign to a manifold a functor. Now the functor is defined on the category of smooth U families of one-dimensional spacetimes and takes values in the category of not U families of star algebras, but U tilde times U families of star algebras. So there's an additional parameterization, yeah? This additional parameterization is precisely what encodes the smooth family of AQFTs, yeah? Again, we have naturalizers witnessing pseudonaturality subject to coherence axioms. So now think of the global stage of this pseudonatural transformation. And this gives you a smooth U tilde family of AQFTs, yeah, in the sense that you have the usual category of one-dimensional spacetimes, but the target is no longer the category of star algebras. It's the category of U tilde smooth U tilde families of star algebras, yeah. And furthermore, so this is kind of the parameterization of your AQFT. Furthermore, there's the structure that tells you how this assignment is itself a smooth assignment. Yeah, you have the other stages which tell you how this thing responds smoothly to smooth variations of geometry. Yeah, so you can vary your AQFT varying parameters in U tilde, but you can also let the geometry vary and see what happens. Yeah. This you can do at the same time, simultaneously. There's an additional structure that we can interesting structure that we can extract, which we didn't mention before. And this is so usually you can take AQFTs, and it's an interesting question to study what are the automorphism groups of AQFTs. These are kind of the symmetries of your field theory. Yeah. Usually you don't know much about the group of symmetries of your AQFT. It's an algebraic group. I mean, not even, it's a group in sets, yeah? It's typically just a group object in the category of sets. So you know nothing about its smooth structure, for example. You have to work hard if you want to say that it's a Lie group, and you have to work example-wise. Yeah, you have to pick an example and study your example and figure out what is the smooth structure, the Lie group structure that you can define on this automorphism group that you have. In this context, you get for free a certain type of smoothness. Yeah. So how do you define the smooth automorphism group for a smooth one-dimensional AQFT, which we said is encoded by a stack morphism of this type? You define it as the loop stack. What is the loop stack? It's just a bicategorical pullback. So you have your point and you have your point. You use A to map inside your stack of AQFTs, and you look at the bicategorical pullback of this, which kind of detects all pseudonatural transformations, all pseudonatural transformations of A which leave A fixed. Yeah. This is this out A gadget. A priori, it's a stack because you take this, you compute this guy inside you compute this bicategorical pullback inside the two category of stacks. So what you get is a priori a stack. Yeah. But this stack, because you have point here and point here, is discrete, which means it's just a sheaf. Yeah, like a discrete category is a set. Here, a discrete stack is just a sheaf. And this sheaf, by the universal property of the bicategorical pullback, also is equipped with a group structure. So it's a group object inside the category of sheaves. According to our jargon, this is precisely what a smooth group means. Yeah. So we have like smoothly parameterized family of groups of automorphisms of our objects. Yeah. That's kind of the payoff we get. So I see that I still have at most 10 minutes left, right? So let me just say how to, let me just sketch how to construct linear examples without going into the details. I was expecting not to have enough time to go through everything, hence I designed my slides in a way that allow for this. So in order to construct linear examples, one needs three inputs. The first input is smoothly parametrized families of vertical differential operators. Yeah. So you kind of look at a smooth U family of manifolds, hence a locally trivializable fiber bundle pi. You look at smooth functions on the total space, but you only consider differential operators that act vertically on the fibers. Yeah. This subscript pi is because you want to think of this gadget as a sheaf of modules over smooth functions only on the base space. Yeah. This is why there's this subscript pi, and this smoothly parameterized between quotation marks means that P is a morphism of C infinity modules over U. Yeah. So sheaves of C infinity modules over U. This is the me not going into the details later on. Yeah. Explaining what the quotation marks mean. Again, you need, as usual, a retarded and advanced green functions, but you need retarded and advanced green functions being smoothly parameterized again. Yeah. And this smoothly parameterized means that you want them again inside the category of C infinity modules over the manifold U, over the base manifold that provides the parameterization. Yeah.
So Marco, so when you're talking about the vertical differential operators, you mean in the direction of these time intervals?
Right, yeah.
So you have this family parameterized by U, or your open sets, and each fiber is like a time interval, and you have differential operators in these.
I mean, the obvious example is you take second derivative in time, yeah? But the time changes pointwise according to the geometry that you provide. I mean, the last line of this slide is precisely this thing, yeah? The third input that you need is well-posed initial value problem. I mean, input 2 and input 3 are typically not really independent of each other, yeah? The usual situation is that you have a good definition of what it means for the vertical differential operator P to be hyperbolic in a suitable sense, and then you get 2 and 3 for free, yeah? That's indeed, so what does well-posed mean? It means that assigning initial data gives you an isomorphism, but now isomorphism in the smoothly parameterized sense, namely in the sense of isomorphism of C infinity modules over U, yeah? Sheaves of C infinity modules over U. Obvious example that Igor anticipated. Let's fix, I mean, in field theory, you would call this M, mass. Yeah, in mechanics, you call that frequency, omega. And it's a positive number that we fix. Then to each fibered manifold equipped with its geometry E, yeah, we assign a certain differential operator, vertical differential operator, which we call P subscript pi E, because it uses the verticality and the geometry of E. This is just, you know, the second time derivative scaled according to E, yeah? So Hodge dual, vertical Hodge dual, vertical de Rham, vertical Hodge dual, vertical de Rham, yeah? Plus square of the frequency. And this indeed defines such a smoothly parameterized vertical differential operator, which is kind of the harmonic oscillator with frequency omega, yeah? And you can also define smooth U families of such problems by saying, instead of letting the frequency be fixed, yeah, you let the frequency vary smoothly over your parameter space, U tilde, yeah? Then you get a new vertical differential operator acting now on sections of an extended bundle, yeah, but not extended in the fibers, just on the base. You kind of take the same as before, and you take the Cartesian product with U tilde. So you kind of only extend the base, the fibers remain the same, yeah? Then it kind of looks like before, but there's this additional U tilde parameterization happening, yeah? Which allows the frequency vary smoothly, yeah? Okay, then this is kind of the input, and now the operations you need to perform are sketched as follows. So you first need to define a smooth U family of Poisson vector spaces. What is a smooth U tilde family of Poisson vector spaces? Well, roughly it's like a Poisson vector space, yeah, but it's parametrized by a smooth manifold U, yeah. So if I were to go into the detail, I would have to define a new stack which replaces the category of Poisson vector spaces. It's similar to, it's to a certain extent similar to what we did already, yeah. The objects of this stack are pairs W and tau, where W is a U parametrized family of Poisson vector spaces, and tau is like the Poisson structure on this, yeah, bilinear pairing, which is anti-symmetric, yeah. But now bilinear pairing means bilinear in the sense of C infinity modules over U, yeah. How do we construct this? We construct this by taking the combination of the advanced, so the retarded minus the advanced green operators we had from the previous slides. Yeah, and how do we construct the vectors, the underlying U family of vector spaces? We just take a quotient, like the analog of the usual quotient, but in the category of sheaves, yeah, of sheaves of C infinity modules. There's a subscript here, which is the vertical analog of compact support. Yeah, so this is compact support on the fibers only. Yeah, it's like you take a section of your manifold pi. You have your fibration pi. You take a section. You take a later section, and the support sits in between these two sections. Yeah. It's like compact only in time, yeah? There's no requirement instead with respect to the parameterization. And then you have to do like usual, yeah? Usual, when you have a linear field theory, you construct this gadget and then you do canonical quantization. You impose canonical commutation relations. However, we need canonical commutation relations now as a stack morphism instead as a functor, yeah? And this, again, I won't have the time to go into the details because my time is already over. You get, when you apply the U stage of this canonical commutation relation stack morphism, you get a quantization of W tau, yeah? So now suppose you have your, let's go back to the previous example. And remember also the U family, the U tilde family of examples. You play this game and you get the quantum harmonic oscillator with frequency omega, yeah, as a smooth one-dimensional AQFT, global object of this stack AQFT 1 infinity. You get the kind of pseudo-naturality with respect to U because this differential operator is natural enough, yeah. If you change geometry, this changes compatibly, yeah? And applying the same construction to frequency parameterized by U tilde, you get a U tilde family of one-dimensional AQFTs, which is a smooth U tilde family of quantum harmonic oscillators, yeah? No more, no less than this. I mean, it's a very easy example, of course. So let's skip over all of this because these are the details which I don't have time to address. And let me mention the open problems. So the open problems are obviously related to go beyond dimension 1. The first problem is a problem in geometry, which, I mean, there are obvious ways how to define the higher dimensional version of the stack log infinity. So for m larger or equal than 2, there are definitely obvious definitions. For example, it's clear that one takes, again, locally trivializable fiber bundles with typical fibers now being m-dimensional instead of one-dimensionals because the fibers have to be your space-time, right? It's clear that you, again, want a certain type of vertical geometry. It's clear that you want fibers to be globally hyperbolic spacetimes, but it's probably also clear that it's not enough to just give the pointwise condition, yeah? because you want to have a certain control, certain in some way uniform control when you compare how two close to each other fibers are globally hyperbolic. You want them to be kind of comparably globally hyperbolic. You want their cones not to be too different from each other in a sense. Yeah. The goal of this uniform kind of property is to get a result that sounds like follows. Yeah, if I give you a decent definition of vertical normally hyperbolic linear differential operators, then you prove a theorem. Those admit smoothly parametrized green operators and the well-posed initial value problem. Yeah. So this is kind of the selection criteria for this uniformity that I cannot. I mean, I can on the nose give you candidates. It's harder to prove that the candidates provide the correct outcome. Yeah. Then there's a question in analysis. So the question in analysis, which I mean, you didn't see this because I couldn't go into the details, but there's a technical aspect. At some point, if we were to go into the details, we would notice that in order to prove that our construction, the construction we outlined of examples of linear, smooth, one-dimensional AQFTs actually defines one, requires to check that a certain family of natural transformations is actually a family of natural isomorphisms. In one dimension, it's easy to prove this because initial data are a free rank 2 object in the category of sheaves of modules. When you go beyond one dimension in space-time, then this is no longer true. It's infinite dimensional. The initial data are infinite dimensional, are obviously infinite dimensional. You get functions. You get functions on initial value surfaces. Yeah. And there are two obvious ways to address this question. One way is to replace sheaves of modules, algebraic sheaves of modules, by topological or bornological sheaves of modules. This gives you certain tools to tame the infinite dimensions. Yeah. There's another option, which is enlarge the two categories. I mean, retain. You still want to work algebraically, but then you don't know anymore if these natural transformations are natural isomorphisms. And you can do the following. You can simply enlarge the two category of stacks by allowing for lax morphisms. Yeah, you give up on the requirement that certain things are isomorphisms. So your question concerning groupoids becomes even more interesting. Yeah. And then there's the last question, which is the one I would like to address first, actually. It's involving Einstein causality. So when the dimension is higher than 1, Einstein causality is no longer trivial. It becomes an actual requirement, a serious requirement. Yeah. There's a smart way of encoding this requirement, which uses operad theory. There's an operad that controls AQFTs in all dimensions, and one interprets AQFTs precisely as algebras over this operad. The analog of what we did so far is construct a theory of stacks, not of categories, but stacks of operads, and then produce AQFTs as mapping stacks, yeah, but stacks of operads. This becomes more involved because operads are not a Cartesian closed category. They are not Cartesian, yeah, and they provide a closed monoid. They have a closed monoidal structure, but this monoidal structure is not Cartesian, and this makes the construction of the mapping stack, most notably the proof that the mapping stack is actually a stack. So you have a candidate how to define it, which is a naive candidate. It's harder to prove that. It's more tricky, but possible I believe, to prove that the mapping stack construction, the analog of the mapping stack construction for stacks valued in operands again provides a stack. Yeah. So again, you have descent in the category of operands. Yeah. Okay, that's it for my side. And yeah, I was late anyhow. Sorry.
Okay, so let's thank Marco. Okay. Any questions? Please feel free to unmute yourself. So please go ahead if anyone has something to ask.
Probably scared everyone saying too many times.
So I should ask us a question, yeah? So
Yeah.
you say that you consider all of the smoothness in terms of the smooth family.
Yeah.
But you consider category of the space, right? And you describe the morphism very briefly at the beginning.
Yeah.
And then, of course, is a space. I assume that's once you consider smoothness, you also should assume the smoothness on this space, right? Or you just ignore.
I think I didn't understand the question. Can you try again?
I say this so that I say that a smoothness. Of course, you have physical motivation, but I consider from the geometry, yeah. Problem.
Let me go back.
And then you extend, then you consider from the beginning that category, that means that's a category of space to the algebraic, yeah, category, quantum field. And on the space, of course, you can ask, because of that in physical, where you have the physical describe our physics one, right? And the notion of smoothness is very natural, right?
Mm-hmm.
And then, of course, you already assume from the beginning that you have some smoothness on this space, right?
Ah, sure. This lock one, yeah?
Yeah.
This is what you mean. Of course, yes. I mean, when I say manifold, I always mean smooth manifold, paracompact, whatever else, yeah? The usual housing paracompact, finite dimensional manifold.
Yeah, and on morphism smooth, because I have to say, of course, you can extend it using the different approach of the how to understand smoothness, yeah, in more synthetical geometry or diffeology or something like that.
Ah, okay.
And there's a second thing that's actually also that's a very important question, because if you consider the infinity that's smooth, I mean that's usually you consider really smooth infinity differentiation is different from the only p time differentiation, because Cartesian closeness or not, yeah. And then that means you and then for example, many people in physics school like Vinogradov, they only assume everything is smooth infinity, because if you assume that only one time t time, then you have to use a lot of functional analysis, right?
Sure. Yeah. This is kind of washed away. I mean, this is not different. This is not so far away from working with diffeologies. Yeah, diffeologies are kind of the concrete objects, are kind of the concrete sheaves on manifolds. Yeah.
Right.
Here everything is kind of infinitely many times differentiable.
Yeah, so such easier.
Yeah, definitely.
Yeah,
definitely.
okay.
Yeah, so this is kind of, if you want to think about this concretely, think of diffeological spaces and the usual definition of smooth, infinitely many times differentiable morphisms between those. Yeah, but in order to, I mean, it's easy from a category theory point of view, it's easier to just give up on the objects being concrete objects and simply work with all sheaves, yeah, because otherwise it becomes much more complicated to perform constructions like limits and co-limits. Sometimes it works. For example, in diffeological spaces, it would work. Yeah.
Yes, but that's very important. I mean, that's considered. Yes, is a limit or co-limits that very important. Yeah, so you can then perform this operation here.
Mm-hmm. I did perform certain operations. Yes, I assumed, for example, you didn't see that. Yeah, so I mean, you saw this incidentally for a second here. Let me come to this. For example, here I took this quotient. Yeah, this quotient is a colimit in the category of sheaves of C infinity modules. Yeah. But this could be performed as well in diffeological spaces. The question is now, which, I mean, you have to decide on the type of diffeology that you want to put on this gadget, for example. I could do this even in bornological spaces or in topological spaces, but then you have to decide, do you want to have for example, separated bornology, completed bornology, plain bornology? This can make a difference. Yeah, sometimes it makes, I mean, generically it would make a difference.
Yes, so thank you. Yes.
Any other questions?
Yeah, I would like to ask why actually, from which I probably missed it, from which assumption do we know the existence of this pullbacks, of this automorphism group defined as pullback? We know it from?
The two category of stacks is complete and co-complete. In particular, it has, I mean, these things are very easy to compute. Yeah, it's called a homotopy pullback. Yeah, one model to compute it is you take an object here, you take an object here. I mean, you do the calculation stage-wise. So you fix a manifold U, and then you evaluate this diagram on this manifold U. And then you say you take an object in the category here, an object in the category there, you map them down here, and you look for an isomorphism comparing them. This gives you an object of the bicategorical pullback. And then if you want the morphisms between two objects, you take a morphism here, a morphism there, and you require that so a morphism here on the first component of the object, a morphism there on the second component of the object, such that when you go down, they agree, yeah, compatibly with the morphisms that you had in your, I mean, the third component of your objects, which were isomorphisms, yeah, comparing the first and the second component. This is kind of, I mean, it's very easy. Yeah, it's very easy.
So even here, putting some topology may cause a problem. Yeah.
No, this sure. I mean, if you put some topology in what now? I mean, if you redefine where would you like to put topology? Would you like to have like categories enriched in topological spaces or something?
Already on the algebras and then induce it on the maps? Yeah.
So it's. I mean, I don't know if what you get is again morphism of stacks, for example, when you put this additional structure. Yeah, this one has to check. I mean, these are checks that I would do example-wise. What I described here is kind of a generic framework where you can do these things, and then it's a different question, at least for me, or an independent, interesting question, is how you kind of find examples inside that fit inside this framework. Yeah, I give you a big box which contains kind of all the, in my opinion, desirable gadgets. And then it's another independent, interesting question, which I very briefly addressed in one simple case, which is the linear examples. But it's a question how to pinpoint examples in there. Yeah, and this is indeed.
I had a further question or some remark. It's quite interesting that you define vertical Hodge.
Yeah.
If one knows only, I don't know, Hodge for Riemannian or for Hermitian structures,
yeah,
you define it via this one form. Yeah. So
yes, I mean, because
use this identification as a, so it's for geometers, this is called probably connection, this E. It's kind of connection form.
I'm not not sure. I mean,
soldering
this is not a
form,
vector
but,
bundle, what I'm talking about.
If you take E times E, you get the metric on the one dimension.
Yeah, here in this case, one-dimensional case. Yeah.
This is why it's a one form, yeah. I mean, one form is just a convenient way of describing this
but only in the
data, but it's not an
one-dimensional
intrinsic
setting,
way.
yeah. So
it's a very much non-intrinsic way. For example, the vertical geometry.
Yeah, so you're right.
Here,
It's specific to one dimension.
Yeah,
Yeah.
very
In
much.
dimensions,
Yeah.
you need the real metric.
If I would have higher dimensions, then I would talk about vertical geometry as being vertical metrics, yeah, a vertical metric which is signature minus plus 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 plus.
Yeah, but so, and if you have this G, you can form a connection, like a Civita connection or principal connection, and then you have connection one form. So, but it's only local, and it shouldn't depend on the verticality.
Yeah, yeah, and this connection acts on the section. I see what you mean. I see. I see. Okay.
Interesting.
So, Marco, about examples. Let's suppose that you solve this issue with Einstein causality and you can generalize this to higher dimensions. So I'm just wondering how much work it would be to show that you know, some obvious examples really fit into your framework. So two that I can think of is one is, for example, when you consider nonlinear classical field theory and you linearize it at every point of a background solution, and then you apply the linear quantization to the linearization. So you have a family of linear quantum field theories parameterized by, you know, the background classical solutions. That's one candidate, and another one is well, in our work with Walter Moretti and later Alberto Melati, which built on work of Hollands and Wald on finite renormalizations of weak powers, right? So we had to come up with some axiom that basically required the, you know, we're working on families of quantum field theories and then building free quantum field theories and then building weak powers of their fields, make an enlarged algebra, and to make that work, you know, to have it reasonable properties, we require the smoothness property there. I don't know if you how much you're familiar with it, but so
I'm not very familiar, but I understand roughly what you say.
Okay, so what do you think about how these two examples would fit into your framework?
That you need to you almost definitely need to first of all do something even more basic. Do the linear. I mean, address the linear case already. I'm not very.
Both cases are families of linear field.
Yeah, but you want algebras that are already kind of containing a lot of more complicated data than just the linear observables. Yeah, because because you want the weak powers. Yeah, so that is already quite. I mean, it's not CCR quantization. Yeah.
Yeah, it's one step beyond that. But what do you think might be the kind of difficulties in fitting it into your framework, like showing that it has the smoothness properties?
So first of all, you need most definitely to set up a nice setting for smoothly parameterized initial value problems, which is usually not what people like to do. People are happy when they can prove that their initial value problem depends continuously on data, on initial data. Here you need smoothly parameterized dependence on initial data if you want. Even more, you need that you need to be able to allow the coefficients in your PDE to depend smoothly on the parameterization. This is because the vertical geometry depends on parameters. And I think this is not usually addressed in the PDE literature. Even though I'm not the one who can say this can be done and this cannot be done in PDE theory, but I would expect that this is doable. I mean, it's just that historically people were more interested in looking for the most singular space where they could set up their PDE problem as a variational problem instead of designing what's the fanciest way of setting up a smoothly parameterized initial value problem. Yeah, simply because historically this was the interest somehow. I mean, I don't see that being so much less interesting than looking for the biggest fractional P such that your PDE problem is well posed in WKP. Yeah. This is the thing that you would have to do first. Already at the linear level, meaning already with just substantial, with only linear observables. And when you want to go beyond this, when you really want to have the Vic powers in the game, then you most definitely need a notion of smoothly parameterized family of states for the underlying linear observables. Yeah. And then using this smoothly parameterized family of states, you can come up with a deformed star product, yeah, which probably, I mean, by the usual construction would make sense in a smoothly parameterized sense, because this smoothly parameterized framework is designed to be so flexible that it just works, yeah. It just works when you can write down something that makes sense. It works. Yeah? Eventually, it works. But there are the two complications that you see here. I mean, there are definitely the two complications that you see in this slide, namely smoothly parameterized green operators and well-posed initial value problem. And you have to tame the infinite dimensions somehow. Yeah. Let it be that the solution is topological Bornological modules, or let it be that you give up on pseudo-natural transformations as morphisms and allow for Lux ones. Yeah? And then you need the additional complication, you need smooth families of states. Yeah? Because you want your star product to be a deformed version of the obvious product, which however is only defined on the linear observables. Yeah, the Vic powers are nastier, of course.
Yeah, so I certainly agree that there's this challenge to analysts to say something about parameterized families of hyperbolic equations.
Yeah.
Okay. Any more questions?
Maybe I would have one rather technical question to the smooth automorphism group and its establishment. I quite know about this construction, but I'm pretty unable to see the reason why this should be discrete. Could you explain it?
I mean, it's just because the top right corner and the bottom left corner are points, yeah, and they are points. These are essentially sets. This is essentially a set seen as a stack, yeah.
Okay.
So you just see as objects of the out A, you only see the pseudo-natural isomorphisms of A, or pseudo-natural automorphisms of A, and there aren't any morphisms in between. They are fixed. Yeah.
Yeah. So it's not a most general picture of homotopy pullback with.
But it's equivalent to this, the one I'm saying.
Yeah. Okay. So
this is equivalent to hidden in between brackets.
Yeah, I can see now.
I didn't say that. Sorry.
Yeah.
Out A is equivalent to a discrete stack. Yeah. So a sheaf.
Okay.
Yeah. Sorry. Sorry for that. Yes. Sorry.
It clarifies.
Yeah. Sure. Yes. I mean, bicategorical pullback as a zillion models. You can do the model, you can do the fattest model in the world if you want, and it's. Yeah. I mean, it can be extremely huge. The point here is that this is equivalent to the thing I'm saying, yeah?
Okay. Makes sense. Thank you.
You're welcome.
Okay. So
So, Igor, did you ask Marco to send slide to you?
I will send them.
Yes, so please send us
Okay.
slides. Yeah, and I guess if there are no more questions, we can thank Marco.
Maybe.
Oh, wait.
May I? So I'm not expert on analysis, but in these hyperbolic problems, there are a book written already, and the last one I was reading was a book from Pfeffle and Genoa.
Yeah.
About,
This I know very well.
This is readable also for algebraically. I don't know, so it's quite readable, I would say.
Yeah, I know that book very well. Yeah.
And the Rees distributions, so the smoothness is on the Cauchy data is researched there, and so.
I'm not sure. Igor, you're better expert.
Well, I mean, they do everything in the usual sense where you have one equation and you're just solving one equation at a time. They're not looking at families of equations and trying to solve them simultaneously, which would be needed to answer the question that Marco is posing.
That's
so,
right.
Sorry, so actually depending smoothly on data means more than
It would be like if you have Cauchy data and then you parameterize a Cauchy data by an extra parameter, and you want everything to depend smoothly on the extra parameters. So all these U's that you saw in Marco's are these extra parameters.
About adding conveniently further parameter there.
Yes. You need the extra parameters to be inside your Cauchy data and inside your PDE.
Okay. So
I think that wasn't addressed in the Genoa.
No, it is certainly it's probably not there.
Yeah.
Okay, so let's thank Marco again.
Thanks.